So this is what we're going to be discussing today, which is this performance diagram, which is 1 billion nested loop iterations, thus showing Zig as the fastest of them all. Then Rust and C, they're all really, really close. Fortran did really good. Odin, Dart, they're all pretty far up there. And then at the very, very bottom, you got languages like R, Lua, Python, Ruby, YJIT, kind of what you would, I guess, what people would generally expect to see if you were to measure such a loop, kind of this distribution, the fast languages on top, the slow and interpreted languages more on the bottom. But we are going to deep dive in it, and what we have on today is Casey, who is much better than I am at all these type of things, and he will be able to explain to us perhaps some of the downfalls of this type of approach. What is it really actually measuring, and if this is really even a good thing to consider ever or for any reason. Is that fair? Is that a fair intro?
That is a fair intro, Prime. And I think also, I don't know if you wanted to maybe start with sort of a slightly more abstract comment, which is because you said this and I 100% agree with you. These bouncy back and forth diagrams are not good to begin with. And I feel like you said you didn't want to elaborate, but I would appreciate it if you'd elaborate, because I'd like to know your thoughts on this, since I am not a fan of these diagrams myself.
Okay, so generally, my general elaborations on these ones is, say you want to choose a language that is both convenient and fairly fast. And so you go to one of these kind of items and you see on here, okay, I got Zig, Rust, and C. Okay, those are like hard languages. Okay, go down here and I see that Go and Node are effectively the exact same speed. You can see right here, they're almost the exact same speed. The difference between 1 second versus 1.1 second, right? And so you're just like, oh, I can really just use Go, or I can really just use Node. I like JavaScript, so I should have the same speed as both Go or JavaScript. And this is like a giant lie, and the reason why is that in the Node world, when it starts running, you are going to get some sort of jitting that's going to happen, and something's going to run, and which is going to make this a fairly fast operation. But this doesn't look like any real programming. No one has a for loop as a service, let alone a billion for loop as a service. This is just not real. There's no memory being created, which is a very big downfall of, say, Node versus Go. There's all these things that happen, right? Like even here, Bun is somehow faster than Go, which makes me just have so many questions as to even how this is written, because how it's measured involves running the program, which will take in a command line argument, and then run, measure how long it takes, and then spit it back out, and does it like 3 times, if I'm not mistaken. Now, you have to go, okay, well, when it runs Bun runs and then loads up JavaScript core, and then JavaScript core interprets it. At some point, JavaScript optimizes, and then at some point, JavaScript core is going to run it. Maybe it doesn't even optimize it. I don't even know what it does, right? Whereas Go should just run the thing. So Go being slower already shows me that there's likely errors in this measurement. And then on top of that, that it's going to make people look at these things and go, oh, it's all the same anyways. And it's like, no, it's actually massively different if you were to write a server. Throw in some like handling of requests, and this thing could be 10 times faster, and you're getting about the same difficulty of programming. It just makes people make bad guesses when they don't even know, like they don't understand why these are destructive or not informative diagrams, shall I say. So that's my personal feeling, is always measure real things, don't measure fake small things.
So that's an excellent point. That's even drilled down even a little further than I was thinking. I was just literally thinking at the top level, those bouncing bars that go back and forth, what is that telling? Like, I literally can't read that. I don't know about you, but like you look at it, like you look and there's 2 things that are the same number almost, and their bars are kind of bouncing back, I guess, at similar speed, but I can't tell. It's like it's bad visualization just to begin with. Before we even talk about all the things that you just talked about, all of which are completely valid as well, it's like the presentation of this benchmark already was a problem, right? But so I was literally talking about just the bouncing ball part of it, but all the things you said are true too.
Yeah, sorry, that's what I think is destructive. But yes, I think you're also right on that, which is that it's very hard, like, because if you were to kind of like scroll into it like now, you're just like, wow, things are just moving all over the place, right? Like,
yeah,
it's very hard to see why this one is so much faster than this one, because you're like, it's just kind of off.
Yeah, like, I don't know, like which one's faster. You can tell the bottom's slower than the top. That's about it. But anyway, yeah, for this particular benchmark, it was very, very strange. I guess we can talk about sort of the high-level stuff like that you just mentioned, and then we'll go in. I prepared some things because I really wanted to talk about the sort of some underlying things about benchmarks that I think are important.
I would love to hear this.
So the first thing I would say is this is one of those things where I want to make a distinction between what I would call a benchmark for comparison purposes, and I wish we had different names for these, a benchmark for comparison purposes versus a benchmark for demonstration purposes. And one of the big reasons I wanted to do this stream today, one of the reasons I wanted to do it last week, but unfortunately I couldn't make it, I wanted to do this stream, was that I feel like this is not talked about. And people, I think, get the wrong impressions because they see people doing certain benchmarks, possibly people who they trust doing certain benchmarks. And then they go, oh, okay, that's how you do a comparison between two things. And then they do, I'm going to do that for languages, right? So you look at someone who does some kind of a benchmarking like Agner Fogg or Daniel Lemire or somebody who's a performance expert is doing this. And you see them running this thing, which oftentimes we will call like a micro benchmark, like the things in this that are shown here. They're very tiny. There's almost no code in them.
I'll bring up code while you keep on going.
Oh, yes. There's almost no code in these benchmarks, and that they're actually comparing, right? And it's possible that the person who's doing that is an expert. And the reason that they have created this very, very small piece of code is to isolate some very specific thing that either they're trying to learn about, meaning they're trying to probe some hardware thing by constructing just the right sequence, or they're trying to demonstrate it to you. So I will show these. Sometimes I'll make a little benchmark. I'll be like, here, and we'll change just one thing. Did you see that change? And then I'll say, that change is because of this, right?
Okay.
Now, people take away from that sometimes an erroneous conclusion, which is that benchmark is like proving that thing, or that is something we would use to compare two things knowing nothing else. But that's not true. You wouldn't do that. What that was an exploration or a demonstration, a thing that after already having understood the problem and had a very complete model for what the machine was doing, we then poked at this one thing in a specific way to show it to you or to confirm it for ourselves, one or the other, right?
Okay. Yeah, I get that.
In no circumstance should anyone be using that as a language benchmark. Like, here's how this language performs, right? At the very maximal use of it, you would only want to say, oh, I decided to test this one thing about languages. I know how they all work. I isolated all of these parts of the languages, and then I poked at this little thing, and here I'm showing you how each one handles this aspect of, in this case, loops, let's say. Totally valid. But if you're just like, language benchmarks, here's loops, and then just you show this thing, it's like, no. Like, that is not at all an acceptable way to use that kind of a benchmark. And so I'd like to draw a distinction between that kind of benchmark and the kind of benchmarks that people are then in their head interpreting the results to be. And those are the kinds like that Gamers Nexus runs or Hardware Unboxed, where they're like, we took Harry Potter and we ran around this part of the Hogwarts school and we saw which GPU ran it the fastest, right? And then they show a chart, not unlike, well, they show better charts than that bouncing one, but they show a chart and they're like, the 4090 is 20% faster than the 4070 or something. People look at these benchmarks like this language benchmarks, which are showing not at all what they think they're showing. They're interpreting them as those kind of benchmark. And that's a benchmark for comparison purposes. And that, to me, is the thing I wanted to start off just sort of really underscoring is you have to, if you're building benchmarks, you have to know what you are building them for. And if you're planning to do something like comparison, like let's see how R does versus C in something, you cannot just do, you can't put it out there like it's sort of this benchmark like the Gamers Nexus, like how fast is my GPU kind of benchmark, which is running real workloads that you actually care about, gigantic, massive gaming setups and running them and actually seeing which thing's fastest. You can't compare it to something like this, which is just like, hey, we made a loop and we're not really sure what it's doing. You know what I mean?
Yeah.
So there, I'll just say that first. if that makes sense.
I do. I think that makes sense. And even to the Gamers Nexus comment, they're still comparing a specific spot with a set of specific things that are running and saying in this one simulation, it's running 20% faster. It's not even saying that this card in all cases runs 20% faster. It's like, no, in Hogwarts, in Ravenclaw's headquarters, it's 20% faster. So it's like it's trying to draw a distinction in this moment, in this time. It's very specific. Whereas this was not presented as a very specific thing, but actually as like a generalized thing. And I think that makes a lot of sense because I guess I didn't really think about it from that way. You're taking a singular operation and you're extending it to be the representation of the whole. It's like saying that if you could only see just, it's like the classic old elephant argument where they're like, the argument for relativism where it's like, one person's touching the trunk and they're saying, oh, well, an elephant has a really long nose, and another person's touching a leg and be like, no, it actually has really strong tree trunk-like item, right? It's just like, okay, yes, we get it. Like, this is not a good generalization of what the whole is. It's just, this is a very specific, very narrow test to say what is faster for this one single thing.
Yes, and not even that, as we'll see in a second.
Oh, beautiful.
When let's just talk really quickly before we get into those nitty-gritty details, because the nitty-gritty details I think are very interesting and they are also something I want to talk about. But moving to like what would you want to see? So let's suppose we were doing a benchmark on looping in languages. What would we want to see? We want to see something like Gamers Nexus. Here's again, you look at one of those things, Hardware Unboxed, Gamers Nexus, I don't know, Linus Tech Tips. I don't know who are the people who do these kind of benchmarks for gamers, right? But you look at what they do, and like you pointed out, it's not just Hogwarts even. They're like, oh, okay, we did Harry Potter, and we did Call of Duty, and we do this and that and that, and they show like 41 games or something on that chart, right? Yeah. So not only are they running real things that the gamer actually wants to use this card for, so that there's no like contrivances. They're not just like running little, how fast is
hello
a
triangle
red pixel? Yeah. It's showing a real workload, but it's also showing a variety of workloads, right? And so what we would want to see for a language test is something like that. 40 representative, large, like things that involve looping, that have heavy looped elements to them. Those workloads written in all the different languages and then run. That's what you would want to see, right? And then the person can look at the source to it and look at the performance of it and go, oh, how easy does this source look to me to create? How easy is it for me to read? Do I like the language? And then what's the performance of the language? How much am I giving up versus this other language? That would be very useful, but not like this is not useful at all, as we'll see. So,
can I throw something else in there? Also,
please.
Like saying this is a loop in a language is all it feels a bit stupid. And what I mean by stupid is that I would assume that the slowest part of this entire loop has nothing to do with the loop itself, because I assume the loop itself is an add instruction and a jump instruction, or some sort of comparison jump instruction. Like that's what the loop is. Like, are you actually gaining? So if you do any other workload, it seems to me is like what you're really testing is the workload. You're not even really testing the loop, because I assume the loop shows up very small comparatively to any workload you could even do anyways.
Well, and this matters more than even you would think at first blush, because so first of all, in compiled languages that are going to be generating very efficient code, what you said is kind of literally true, right? Meaning it's going to produce a very straightforward, increment or decrement, depending on how it side structure the loop, and then a comparison and a jump, or it might not even do a comparison jump. It might just use the decrement to do the jump. Depends what it does, right? So it's how creative it wants to be, but something like that. And those instructions are going to be probably hidden in the shadow of all the other things you're doing, and will almost end up being free usually, right?
Yeah.
And so what you risk when you test something like this is you're like, well, you risk testing how efficiently it generated those things because there's no work necessarily. It's not in this particular, because we're going to talk about this loop has some really bad issues that we're going to talk about in a second that make it even worse than this. But I'm saying if you were to construct some even more simplistic loop than this one, you run the risk of measuring something the compiler's doing that you will never actually care about in practice, because if it was slightly less efficient as generating those sort of loop maintenance instructions, you would never know if you had normal work in there. You just wouldn't know because there you have others. The CPU is just going to chew through them and as a sideband thing. It doesn't even look at anyway. So there's that. But suppose we're in a language that's not very efficient, right? Well, then what we're saying makes even more. It could become even more important. Suppose you're in a language where it's like all the arithmetic, including the loop, like for I part, is done in like big int or something, right? It's like the language only has doubles and the loops are done in doubles. Or like who knows, right? You could imagine some weird things about languages that would come into play here.
Yeah.
Well, then when you measure the performance of this loop, it's going to be like, oh my God, like the loop overhead is massive because it has to do all this extra work on every loop iteration. But then you realize, well, okay, the loop overhead, though, for this language won't be all that massive compared to what the loop's actually going to do, which is going to also have to do all that stuff. So it's like, yes, that just means this is a relatively slow language, but it wouldn't necessarily tell you anything that like the loop performance of that language needs to be improved, because that's not really what's going on. What's going on is you're just writing in a language that has very expensive integers, and you have to understand that or be okay with that. You had to have chosen that, right? So again, even in that case, where you think it's telling you something, it's really possibly misleading you even then.
Interesting.
And so I just want to get that out there, that it's like when you don't have a loop body that's actually doing anything, you draw very odd conclusions about what's going on, and that's just not a great place to be, right? So we'll say that.
Interesting, yeah. I actually never even thought about even just the integer representation could be an expensive or inexpensive thing. I mean, JavaScript only in the last, 5-6 years got SMEs, small integers, where they don't actually have to be heap allocated. They're actually just a part of the heap address instead with a little tag in front of it. Okay. And so like
Yeah.
those are
Okay.
just fundamentally cheaper because now they're just they're the thing as opposed to a pointer to the thing. And so that could be
Yep.
a massive difference between languages that say don't ever have that, any sort of interpreted language. And so I never even thought about that. That's really interesting.
Well, let's dive in then. I
Yeah.
assume, unless you have any other stuff you want to talk about high level.
No. We could
Okay.
do a code review of emoji code if you want to at some point. Since I added
I'm
it.
totally happy. You're gonna have to explain it all to me though, because I do not know emoji code.
Oh, I know it. I only know how to read it.
All right,
I'm going to put you big
okay.
screen.
Okay.
You can cover me too. I'm not too worried about being covered.
No, okay, you got it. Where are you, Prime? You're not there at all?
I'm not there at all, and I think it's okay because we got to keep you on.
No, we gotta have a Prime face. It can't show up above. Maybe if it can't. That's fine with me.
Of course
I
it
guess,
can, but hold
there
on.
it is. Yeah.
Here, let me make myself
Yeah,
real small.
yeah. That's what we want.
There you go. Hey,
Yeah,
look
yeah.
how small I am now.
Perfect.
Now I got to do one more flipping again.
Just you gotta flip every time.
Whoop. There you go.
Yep. Okay. So here is that source code that you just had up. This is for the C version.
Could you zoom in a
And-
couple times for us?
Yes.
Yeah, typically you want to pretend like you have really bad vision when you're on YouTube.
Is that good or?
Yeah. I think that's fine. Is everyone fine with that? I think everyone is generally fine. People are saying,
Okay.
what is this IDE? People just they can't handle the Notepad++. They just don't have that energy.
This is not an IDE or anything. It's just Notepad++ so I can show some code snippets.
Yeah.
I don't use Notepad++ for programming. I do use it for this purpose though, if I'm pulling up random things. So that part is true.
Okay, I'd first like to start off with a knit. Obviously, you have a space between function name and parentheses. I find this to be completely rework the whole code.
I do or they do?
They do. Well, whoever has it
think
on
they
here,
do.
triggered. I'm
Yeah.
completely triggered right now.
I don't think I never do that. So that's them.
Okay.
That's whoever submitted the C benchmark code here.
Okay. All right, sorry for
So-
interrupting. Let's start.
No. So if we take a look at this code, right? You can see that I'll explain the general structure of it really quickly. And I can also explain sort of probably why it looks the way it does. I'm guessing what happened here, I'm just imagining in my head. What probably happened here is when they were writing these benchmarks, what they found is that, quote unquote, AOT languages, right? Like ahead of time compilation languages like C, like Odin, like Rust, probably things like Go as well. I'm not sure to what extent I don't have much experience with Go,
Yeah,
but
Go's a ahead of time compilation.
it's ahead of time, and so I assume it would do this. I just don't know if it does or not. But those languages, that go through LLVM backends and stuff like that as well, what they're going to do is they're going to eliminate these loops pretty aggressively. So if you don't put something in here inside the body of the loop that is unpredictable, right, then these loops will just collapse. The compilers will just look at what you did, run it, basically, produce the result, and replace the loop with the result, right? So what you can see them doing here, and I do not fundamentally understand why it looks like it does here, maybe for other languages, but what they're doing is trying to get external information that cannot be predicted and to use that in the body of the loop so the loops won't go away. So you can see them, one thing they're doing is they're reading a integer from the command line. In C, for those of you who don't know, these are the command line arguments here, this argv. First one, 0, is the name of the executable. The second one is the first thing that the person put after that. So when you type it in, so here you can see them, they're reading it in, they're converting it to an integer so that they have a value, u, that is not known to the compiler, right? The compiler can't know what u is because it comes from the user. And they're using that as a mod, with the modulus operator here. So it's doing a divide effectively by u. So that is their first attempt to make sure that basically the body of this loop is not optimized away. Does that make sense?
Yep.
Okay. And then for some unknown reason, and I don't know why, because one value should in theory be sufficient, or if you wanted another one, just read the next argument. They then go ahead and ask the random number generator to produce another one for them. And of course, the random number generator would produce a known value as well if you didn't first seed it with something unknown. And that unknown in this case is calling the time function. So what time of day is it? Seed the random number generator with that. Then we generate a random number. And that gives us something for our outer loop to be adding, which is this R here. And it also does one other thing, because you'll notice they decided, again, I'm not quite clear why, probably again because they were trying to have the loop do a certain type of work and they were trying to figure out how to not get the loop optimized away. They're keeping an array of 10,000 items, and this loop updates, like it writes back to all 10,000 items. The outer loop loops through all 10,000, and you can see them getting written too, right? At the end, they select a specific one of those 10,000 items using the random selection that they pulled here. And again, my guess is the reason they did that is because if they didn't, the compiler would notice that those values were all unused except for the one that you ended up printing out at the end and throw them away. Make sense?
Yep. That's what I assumed all this was for, was exactly all those things, to avoid any sort of weird compilation.
So there you go. That's what they're doing in this loop. Very, very simple stuff, but that's what they're doing, and I think it's all because of that. If we look at the actual loop, inside the very interior of the loop, what they're doing is for, in the outer loop, they're selecting one of the elements. They're doing the elements in order. They're selecting one of the elements, and for that first, for whichever element they're picking, they're just doing a summation. So, for 100,000 times in the interior, they're going to sum into that location the sum of whatever the loop count is, so J in this case, divided by that number that came in. They're doing the modulus, so the remainder effectively. It's not quite the remainder in C. It's modulus in C the way that it handles negatives is slightly different, so I don't want anyone to get confused there. But basically, this is like computing the remainder, right? It's like the remainder of the loop count divided by this thing that came in, whatever number they picked. So that's all the loop's going to do, right?
All right, we're following. By the way, isn't that always the same number?
Which one?
J modulo U, the summation. Doesn't that sum produce the same number every single time? Because it's J modulo U, which is kind of like for 1 to 100,000 would produce the same J modulus U every single time, starts at 0. It's actually just like a constant once it's computed once.
Now that you mention that, Yes. And that is very strange because you know what? I don't think I've seen any compiler notice that, Prime. You're better than all the compilers.
I knew I could defeat a compiler. My friends have always told me I've defeated the compiler before, but it's never been a compliment. This is very nice.
Because they don't update you like you would. What you would probably want to do here. I mean, there's many things you'd want to do, such as not write any of this, but you would have to update you here somehow, right?
Yeah.
And no, they
Yeah,
don't.
you'd have to update you by some sort of amount such that every time it runs, it doesn't recompute 0 through 1,000 moduloed by you or 100,000 moduloed by you every single time. Because that's just a sum of the same thing. Yeah.
You're right. And, I don't think... I mean, I guess now... Hold on a second. Sorry, we're jumping ahead briefly here, everyone. I don't think the compiler does that, does it? Maybe they did, and I just don't know about it. No, they don't. So, sadly, Prime, you're probably going to have to... I don't know... So, technically, I don't know what your role is at the company, the terminal.shop company, but you may have to resign and go work on the LLVM team, because I'm pretty sure they didn't catch that.
I don't think they caught that hole. And there's a bunch of people being like, oh, no, J is, edited by J++. Okay, for those that aren't understanding what's happening here, think about this for 1 second. Use a constant. Let's just call it 42. And you're going to take 0 through 100,000, and you're going to take a modulo of each one of those values. And you're going to sum that starting at 0. If you were to do it again, it should produce the same value. If no matter how many times you do it, taking 0 through 100,000, summing each one of those values moduloed by 42, is going to produce the same value every single time. That's what that loop is doing, because U never changes. J is the same value every single time. It goes from 0 to 100,000 every single time. A sub I always starts off as 0. So for those that don't really get it, you're just, there you go. Thank you very much. That's exactly it. That produces the same value every single time, no matter what you do.
Yeah. So Prime's just saying, look, just make one loop, separate these loops, pull this loop out beforehand, produce the base value, then do a for I loop here to 10,000, writing the base value plus R.
Which is also another constant value at the plus.
Into the thing.
This is so good. You could have just started base value as R.
Yeah. I was just focusing on the codegen side. I didn't even look at that part of it. But as you were saying it, Prime, I'm like, wow, this is even worse than I thought.
Okay, but anyway, sorry for the distraction. It's just
that's
you
not a
explaining
distraction.
it to
That's
me
a
made me laugh
perfect
at
example.
that. Yeah,
no, that's a perfect example of what's wrong with this benchmark, right?
Yeah. So the idea could be that it could actually end up getting compiled. So maybe the difference between Clang and LLVM, maybe one of them would actually compile it away versus the other. Who knows? Maybe there's something that would actually catch this as a constant.
Yeah, I now I want to go look and try a bunch of compilers to see if anybody notices that. So that's pretty interesting. Maybe there's a reason why technically they can't do that because of C semantics or something like this.
Yeah.
But anyway, yet again, another reason why is just don't do this, right? Don't create contrived examples as comparisons like this, because the only way that this kind of thing is useful is when you know what you're probing for. When you're looking for a specific thing and you're like testing that very specific thing, which is not what's going on here. So anyway, yeah, that's a great catch there, Prime. I mean, I think it could. I think a compiler probably could go ahead and hoist that and then just rep it out. But anyway. So let's talk about what actually happens here, though. So the biggest problem that you get with something like this is in their attempts to make this loop body not go away entirely. What they ended up doing is they ended up doing a modulus by an integer that is not known to the compiler. Now, this is something that you never, ever, ever want to do. I, oddly enough, see it in people's benchmarks fairly frequently because I don't think people understand just exactly what happens when you do integer divide. Integer divide is like one of the worst operations you can ask the CPU to do that it does natively. It's very, very difficult for the CPU, and there really are no CPUs that you currently would experience. I mean, I guess I don't know about I don't know how bad M series is. I don't know what they've got for a divider on there because I don't have one. But, you know, like in the x64 world where we live, it's just, you just don't want to do it. And just to give you some perspective on that, this machine right here is a bit old. It's a Skylake machine, but I also have the Zen 4 up here. Those of you who've seen me on Prime Stream before know I love to show what the actual instructions are. So the instruction that you're going to be doing here is going to be like an IDIV instruction. That's the thing that asks the CPU to do a division between integers. And what you can see here is this thing under ports, as I've explained on previous streams, I'll just say it one more time for clarity. This tells you how many operations, basically, the CPU has to do and on which of its execution units it's going to have to do them. So for just this one divide, it's going to have to do this. You can read this as 2 operations on port 0. Then, so this plus is like then, or and, 2 on port 0, 1, 5, or 6. Any of the ports could do it.
Okay,
then,
quick interruption. The plus, it means serial, right? It does not mean parallel.
Not necessarily. We don't know.
Okay, you don't know. Okay.
Not entirely serial, but some of them may be serialized. We don't have that information. We typically don't get that information. These are even just this information is found by micro benchmark probing. By doing the kinds of things I was saying before, where we're making things and like poking at it.
Okay.
And 1 on 0 or 6, another one on 1 or 5, and then 4 on port 5, right? So normally, if you look at like an add, it's like 1 operation, right? It's like 1 on 0, 1, 5, or 6, or something like that. So when you do an integer modulus, you basically spam all of the execution ports of like an Intel processor with tons of crap that it has to do. And you look over and you look at the latencies. So these are how many cycles you would expect to get the result back in. So here you see like 23 or something on the ballpark of between 20 and 30 latency, right? So that's 20 or 30 cycles, right? And the throughput, which means how many of these you could like overlap basically. If you were just issuing random moduluses that didn't depend on each other, then the maximum throughput you could hope for would be 6. Okay? So really ugly stuff compared to something like an addition or anything like that, where not only, if you look at something like add, so that we're done with that, I can just try to show you an example. Like if you wanted to add 2 register values together, for example, what you would see there is it's like, not only, click on that. Not only is there only one operation the CPU will have to do, and it can also do it on any of 4 different ports, which means that if you are just issuing these, a bunch of them that are unrelated, you can do 4 at a time. That's what 0.25 means. It means a quarter cycle to do your add. Why? Because it can do 4 at a time. So effectively, any one of them, if you have enough of them and you're doing them in bulk, will only take a quarter cycle, right? So a quarter cycle versus 6 cycles tells you something about the ratio of, the expense, right?
Okay, yeah.
So when we come back here and you see literally what's in the body of this, an add, which as I just said is basically what we would call free, right? It's so free that it's on the order of like the loop increment in terms of what we're expecting the compiler to be, the CPU to be doing. Then we've got this right here, which is this monster of an operation that's going to take, some number of cycles, probably 6 or more, right? So when you look at this, you're just asking the question, well, okay, what are you benchmarking now at that point? None of these languages are really going to be able to do very much about that. Like, they have to run these divides on CPU. As Prime just demonstrated, really all you're going to be benchmarking is to see whether or not one of those compilers was smart enough to take this out and do it ahead of time, right? That's the only way you could really get a meaningful win on this particular benchmark. And what you can see from the construction of the benchmark is they've tried very hard to keep preventing they probably looked, and every time the compiler was able to do something like that, they added a new prevention for it. So not only are they basically creating a benchmark where the only meaningful thing between AOT languages would be what are you actually going to be able to optimize out? But then they prevented them from optimizing that out. So what are we left with? We're left with just a giant string of divides that will just choke the CPU. So that is what you'll be waiting for. And here's the other part of it before we get into the couple other finer points here. And the bigger issue is, what's the definition of modulus in the language? If the language defines modulus to be something that, let's say, throws an exception if it is 0, right? Well, now that language has to throw extra work into this benchmark somewhere to check to see if U was 0. If the language is smart, it will put it up above here. But like, my understanding is languages like Go or something will have or Rust might have a thing in there that go, oh, check to see if that's it. If it is, I have to throw an exception or do a panic because I'm not allowed to actually have the build fault, right? It has to do this other thing that my language defines that is not supposed to go through the fault handler or something, right? That's a purely like you've added something to the interior of this without telling the language that it doesn't have to worry about that. Well, that's a pretty big issue, right?
Okay, yeah.
So there's that, right? So when we look at the differences between these compiled languages, and for some reason they still ranked them, there wasn't like an interval or some like thing that said, well, anything that's above 0.6 is just the same because this is all noise or whatever. So you're timing that aspect of it. How long does it take to do any checking that it has to do? You're timing to see how long the random number generator takes to initialize and run. You're timing how long that language takes to convert ASCII to integer and to retrieve a command line argument, and, right?
Yeah.
So,
and I assume most of those are like, there's so much. I would assume initializing a random number generator and then getting a random number generator and moduloing that by 10,000 is like the same equivalent cost of doing 10,000 for loop iterations. Like it's just like massively huge comparatively. That it's just like it's huge.
It's not, but it's not nothing, and that's why you see that separation at the top.
Yeah.
Right. Is there all these other things, and then the checking, right? And what's more, depending on how we define modulus, you may have to do extra work in here too, in the body of the loop, to produce what the actual answer is, because maybe modulus is different in your language. And we're not even getting to the part where, oh, in some languages, modulus might be infinite precision, like we talked about before, right? So maybe, and then you're into a whole nother world of herd, right? And who knows, right? So there's all this other crap. Infinite precision is the wrong word, but you know what I mean? Like big int or something like that, doing weird stuff with modulus, who knows? So again, really, really bad, but that's all just me talking at you. What I wanted to show now was just how ridiculously weird this stuff is and how it doesn't really capture what you would want compilers to do anyway, and et cetera, et cetera.
Can I interject for one quick second?
Please.
If I'm not mistaken, with JavaScript, if you have the small integer requirement can exceed 2 to the 31, if I'm not mistaken. And in this loop, you may accidentally exceed 2 to the 31. I don't know how big U is or what the actual final value could be, but you could theoretically go from a SME, which is going to be much, much faster, into an actual like heap stored int. And then I believe once you do that, it could change all of them. I'm not exactly sure how all those things work. There's like a whole dance around optimization of integers as you're talking about that prove your point, which is very fair, which is handling ints can be very expensive.
It all depends on language semantics. And again, so again, if you were trying to demonstrate that, if you're like, let's look at numerical language, semantics of numbers in languages, and I want to benchmark that and what the costs are of that, great. If you know what you're doing and you understand all the languages and you show it clearly, that's good. That's information people can use. What you're doing here is calling something a looping benchmark that actually doesn't really have anything to do with looping.
Yeah.
Right? That's what's actually going on. We're not really...
The loop is
not
kind
really
of
what we're talking
just
about.
meant to make that work happen a long time.
Yeah.
Right.
So anyway, that's one of the biggest problems. But another thing that I just wanted to point out here is, so let's suppose that we did want to benchmark. Like now I'm trying to move it from like negative, like please don't do this. Like this was bad. This is not a good benchmark. Please stop. Let me shift it to just demonstrating why I think it's important to understand what's going on and say, if we did want to make a looping benchmark, micro benchmarks for looping, what would we actually be looking for? And why is this not it, right? So at that high end, you saw there was all these languages listed there. There's like, Zig and Odin, Rust
C,
and C and Java, not Java.
C# was actually really high up on that list. Yeah.
Basically languages that can do loops, that will JIT loops to something sensible. They're all up at the top. Well, languages aren't all created equal, even up at the top for looping. And what you actually want to measure, like Fortran would be an example of one that has good loop semantics or something like that, right? ISPC would be one of the best examples, right? Which is now sort of built into CLLVM. I don't know the specifics of where it migrated to, but if you look at something like this, normally what we're looking at when we look at loops and we want to benchmark them, and again, I think this was lost on the people who made the benchmark because they're thinking kind of old school programming, like 1990s style programming. Modern loop benchmarks should be about vectorization, right? When you're looking at loop performance, the only time you would really be caring about loop performance, you want vectorization. Like it needs to be vectorized if it's going to be fast. So we want it to take things that we write in scalar, right? Meaning we are just writing things that look to us normal, like AI equals AI plus J mod U, right? And we want it to turn them into things that are operating wide. So on many values at once, using the SIMD, the power of, AVX 512 or something, inside the CPU, we want it to be doing that for us. That's what we would be benchmarking for language, for looping, right? Now, what they've done here is they've made it so that's not possible, because by doing a modulus, what you've done is ensured, more or less, that unless the compiler is incredibly squinky, it's not going to be able to vectorize because, again, like I said, anytime you see a modulus or a divide by a number that isn't known, if it's known, that's okay because there's other things can happen. But by a number that isn't known, it's a huge, huge red flag, as the kids today say, because the CPUs today don't have divides that operate wide. So if you look at like vector instruction sets, they typically don't have a divide because it's, again, you saw how bad it is to do. They oftentimes just don't support that. Not that we wouldn't love to have it. It just isn't in there, right?
Is it because the number of ports that can perform it and the length of it just make it so that it kind of like defeats SIMD itself, or what's the problem? Because I don't quite understand it, I guess.
I don't know, but I guess here is a, if you want an answer that's almost certainly wrong and you should ignore, my assumption is because in order to do a divide in a reasonable amount of time, you need a lookup table, I think, or at least used to. This is maybe, like I say, it's old. And they probably don't want to bake those lookup tables into every lane of the SIMD thing. They do for things that really matter, like reciprocal or reciprocal square roots, those sorts of things, because those are really common in highly optimized like vector math stuff. But they don't, as far as I know, they don't do it for integer divide, right? Okay. They will do it for like floating point divide because floating point divide matters to the benchmarks, but because people don't do integer divides in math benchmarks, they're not gonna, I don't know, put that work in to make it. I don't know, to be completely honest with you. I really don't. It would be great to have a hardware engineer tell us why they don't want to do it, but obviously they could. It's too expensive for them to want to do, I guess. So anyway, but I'm glad you mentioned that, because the next thing I wanted to show you is some kind of weird things that happen here. So let's take a look. I'm going to show you the assembly that's produced from this now. So this is using Clang 15, which is the same version that's installed on this machine. So if I can run this thing. I built this on my machine.
Nice.
And I have theirs, like Code Orig is what I called for original, is the one that they ship. So the one that we're looking at now. This is the thing, Hyperfine, they're running. My machine is old. This is a machine from 2017. He was running it on like a modern M series processor, so his is obviously faster. I think his was 0.5,
Yeah,
right?
something like 0.5, yeah.
Right, like, and on mine it's 1.734 or whatever, right? So mine's quite a bit slower. But that's running that code on this machine. That's what we get. And what was that running? Well, it was running this, right? It was running this code here. What did the compiler do? Well, you could see that effectively what it did is it unrolled the loop, right? IDiv, 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 IDiv. It unrolled the loop 4 times. And then it does, remember you were saying, what is the loop? You said it's an increment, a comparison, and a jump. Well, here's your increment, comparison, and jump prime. They're right there just as you anticipated they would be, right? And you can see it's adding 4 instead of 1 because it unrolled the loop 4 times. So it's going up by 4, right? It's comparing to see whether it's hit that cap, right? What we told it to go to. And then it's jumping back up to here. So it's doing the divide.
Can I ask a stupid
right?
question?
Yeah, there are no stupid questions in assembly language.
You just wait. But why 4, not 8? Like, is there some sort of magic to how many you want to do before it's actually better to do the jump?
Well, to be completely honest with you, because this question was investigated slightly by me beforehand.
Okay.
To be completely honest with you, I'm not sure what the internal metrics are for Clang. One of the things you have to remember, and I don't know the specifics of what it does internally, but there's all these like things. I don't remember what the is it M something like minus M AVX2? Yeah. There's all these settings that you pass potentially that tell it about what level of machine it's operating on, right? And I don't know, because I don't spend a whole lot of time poking at the optimizer in Clang. I don't know to what extent this unrolling level represents some kind of average best guess for how many times it would make sense to unroll something, given that it doesn't know exactly which x64 processor you're running on.
Okay.
Right? 4 isn't probably optimal. I think 8 would have been better, actually, in this case. And again, it's because, at least I believe, these IDivs, because they're flooding so many of those operations in there, if you can have more of them in flight at any given time, it helps to make sure you're maximally utilizing all those ports and not waiting, right? Because you want to try to make sure that this sort of you've got all these ads happening, right? And the ads are kind of adding into a single value, right? And because those ads and that IDiv are all using the same ports as this ad here is going to be doing, and this comp, unlike a normal loop, you are actually potentially contending for resources with your own, with your own loop maintenance, right? Which normally we wouldn't expect. Like, that's not what we would normally expect. We would expect like some loads and stores in here that would, be taking time and using different ports. We would expect some vector operations in here or floating point operations in here, something to take the pressure off of the 5 adders or 4 adders, depending on which CPU you're on, right? But that's not the case. So because the IDiv is spamming those adders and the ad is spamming those adders, and there's really nothing else here, unrolling actually helps.
Okay.
So I don't know how it decided 4.
Okay.
4
I
is
assume
not
some level has to, because you can put more than one instruction can be in flight at any one time. So I assume some level of unrolling has to help, because I assume the jumping defeats the multiple instructions in flight, correct?
No, and
Okay.
that is why
Dumb
I
question
was
number
trying
one.
to.
Got him.
It's a very good question, actually. So what happens with this code in the front end of the CPU is the front end is going to assume that this jump happens. It's just going to assume that. So what you're actually going to get flowing to the back end is just an infinity of copies of that.
Okay.
So it's as if you unrolled it a billion times yourself anyway. So all that's really happening when you unroll the loop is you're saving these two operations, right? You don't have to do 4 of them now. You only have to do 1 of each.
Okay.
Right?
Yeah. Okay, that makes sense.
And normally, like I said, again, one of the reasons it's such a bad benchmark, normally you wouldn't care about that. Like normally you have spare adder, right, capacity to do an add comp jump like that. So it just doesn't matter. Like those ports, those execution units are just sitting there not doing anything anyway. They're not under as much pressure as everything else. So you just have them and you don't care. So typically you don't need to unroll a loop for that reason, right? But in this case,
can I ask you to execute one more set of commands? I've seen this pop up in chat like 50 times now. People are saying dash march equals native. I assume that's machine architecture equals native. Dash march equals native.
Colon native?
No, just equals native.
For Skylake. Or wait, but what's it going to use? I don't know what Godbolt's native is.
Neither do I, but people keep saying it's going to do something different. It's going to make a bigger unroll, maybe.
Yeah, so there you go. It unrolled it a little more, right?
Okay.
2, 3, 4, 5, 6, 7, 8. So it picked 8 as I predicted, right?
Okay, so it's effectively this. It's able to understand whatever machine it's running on more inherently with that.
Yeah, well, that's why I said like, I don't know the switches very well. You probably don't want March native. I mean, for a benchmark, you might because you might want to be interrogating your own machine. I don't know what a sensible thing is to pass here these days. Is I guess what I'm saying. Right?
Yeah.
Like,
okay,
what should you probably pass here? Clang experts would know. They'd be like, oh, you probably want blah because it's a good mix of like targeting Zen 4 and 5, but also not bad on, I don't know, right?
Okay,
but
and the purpose of all this, just again for us laymen, is that when you're distributing, when you're passing on a distributable, you want to compile it in such a way that it runs on all machines, but it also runs the most optimal. And so by doing something like March native, I'm saying March native for just let me have that. Doing that, it will build it the best for your machine. But you still may run on a bunch of different processors where it actually runs inherently worse. And so it's like there's different options to say, hey, this will run the best on the most amount versus this will run the best on a single instance. And it's like you're flipping these two switches, right?
And that is just not something I ever do, right? Like I always like, okay, if there's a performance critical part of my code that I try to write all my code so it runs pretty good. And then the performance critical parts, I hand tune them usually with intrinsic. So I basically, if I want it unrolled, I'll unroll it myself, right? So I typically don't do that kind of stuff. I couldn't tell you what the best flavors are of things.
Okay.
But the point I was making before, prior to March native, was just there are all these M arch and M flags where you can specify things. This one just tells it can use the more advanced instruction sets, like AVX2 or AVX512 or that sort of stuff. And then the other ones you can say, like for particular CPU cores, like I said, telling it that, it may be like, oh, okay, I should unroll this more, or oh, I should unroll it less, right? And so those are just metrics based on that CPU core that it's using.
That makes perfect
sense.
And
I don't know where it's getting those metrics or how accurate they are for any particular core, but that's what's up.
Okay, so yeah, a lot of these tools are just meant for like if you're running a heavy workload on a machine you own and you want it to be the most specifically best for this particular machine, then you run it with these extra things. And it's because you own it, you know it, you can really make it the exact way you want versus here's something for everybody.
It for your server.
Yeah. Okay.
You know what the server is. You want it to be optimally performant, et cetera, et cetera. Okay. So that's what's going on in here. And as you can see, there is no vectorization of this loop, right? It unrolled it, meaning it's doing 4 of these in here.
Yep.
But it did not vectorize it because you can see it's still going up by 4. If these instructions were vector instructions, so they were doing more than one computation for the instruction, obviously we wouldn't be going up by 4 anymore. We'd be going up by 4 times whatever the vector width is. If the vector width was 8, it'd be 4 times 8, right? It'd be 32 or something. So we know we're still, and of course, also if you know assembly language, you know that you're not, because you see the instructions, you're like, well, IDIV, that's a scalar instruction. It isn't SIMD. It doesn't take advantage of wide execution. Okay, so that's what's going on there. What I wanted to show was like, well, okay, suppose that, because you were cheeky, the person who you want C to look better on this benchmark. So when you submit it, because the people who do the benchmark don't know, you submit the same benchmark, and you can see this is almost exactly the same code. It's like,
can you hold on just 1 second? My
Right.
dogs are barking, and I got to go figure out what that is. Hold on just
Sure.
1 second. All right, hey, sorry. My dog had like a quarter of a deer carcass and apparently was celebrating. I'm not really sure what's
Wow.
going on out there, so I'm just going to leave it and pretend it doesn't exist.
that sounds serious.
Yeah, I don't want to touch it, so I'm just like, all right, you have it. I don't know what's happening.
All right, fair enough. So if you look here, all I've done, it's the exact same thing, right? All I did is add the math.h include so that I could call trunk.
Okay.
And I replaced this j mod u with doing the modulus in double, right? So double precision floating point arithmetic. I've replaced it so that I take the quotient by literally doing the modulus manually myself. J divided by u, truncate that value, then subtract what the multiplication of that back up from the original value. Literally taking the remainder by like divide, truncate, multiply, subtract, right?
Cool. Yeah.
Manually.
Yeah, that's
right.
This you're getting back to grade school at this point. Let's go.
Yeah, that's right. So suppose someone wanted to, make C look really good on this benchmark. So you resubmit this code and you put in some cheeky comment like, C doesn't support proper modulus, so just trying to make this more accurate or something, right?
Yeah.
Some dodgy comment to sneak it through, right? And by the way, I have a check in here which we can run if anyone doesn't believe me. This will compute literally exactly the same thing. You can run this check and you will get, no matter what you put in for you will get the correct answers here. So if we were to run this code now, well, over here, code double.exe, using the exact same benchmarking suite, and everything, it's like, oh, hey.
It's like 4 times as fast.
Not only do I blow away my own result, but on this 2017 computer, I blow away their result they were getting on an M series Mac, right?
What? That's so sweet.
Right? And so what happened here, right? Let's paste this in and you can see.
You
I'll
should
get rid of
definitely
this
make a
code.
PR for that. It just makes C look so good.
Yeah, right?
Actually, C is the best language in the world.
Yeah, this is why I say this is all pretty stupid. So let's take a look at what happened.
Oh, that's
Look over
SIMD stuff,
here.
right? Is that what's happening?
Yeah, exactly, right? It's exactly what you think. So you can see in here, we're still getting some unrolling happening, right? We've got multiple VDiv PDs. VDiv PD is when you're going to divide. So the way you can read this is V prefix just is a thing that was introduced to patch over some nastiness of the original. That they needed to extend out to the wider registers with AVX and also fix some things about whether or not implicit memory arguments were loaded. So V prefix instructions, you can really ignore the V. The V is a prefix that goes on it for historical architecture reasons you can ignore. So really the instruction that you care about is div PD, and the V is on there because it has to be if it wants to use the AVX registers, the eight wide registers.
Yeah.
So div PD is really the instruction we're talking about. It's divide packed doubles. The packed, because it's SIMD, so there's multiple doubles packed into a single one. D for double, meaning 64-bit floating point instead of 32-bit floating point, right? So what you can see here is it's literally just doing what we told it to do. Adds, divides, and multiplies here, right? And it's just doing a bunch of those. And the round PD is the truncation part, et cetera, et cetera. So anyway, it's doing this stuff. And then this V convert, by the way, also because it needs to convert it to an integer to add. So there's also the part where it actually turns it into an integer to do the add, but that's sort of separate. Okay. So anyway, it's doing all of this work now, but it's basically the same thing. Like effectively, we're doing the same kind of work that we were doing before. It's just now, instead of it having to use the IDIV instruction, it's able to use a few SIMD instructions instead. And because of that, it can now do 8 at a time. So instead of this loop having to go from 0 to 100,000 by increments of 1, or in this case, increments of 4, doing 4 separate ones at a time, which is still the same as doing them one at a time, right? Now we're able to go 8 at a time and unroll if we want to, which it did want to by 4. So we're actually going to go up by something like 32, or who knows what it ended up doing here. Let's see what we ended up actually thinking here. We've got a 16 on that one. Oh, sorry, it won't be 8 at a time. My bad. 4 at a time.
Okay,
why is it 4 at a time?
4 times faster as well. So okay.
Why is it 4 at a time? Doubles.
It takes up 2 spots.
My brain
slots.
My brain is hardwired for float. So anytime I see the VDiv, I'm like, oh, it's 8 at a time. No, it's not. 4 at a time. So I was like, this should be 32. It's not. 16. Why? Unrolled 4 times plus we're 4 wide, right? So off we go, and now we can get effectively, massive performance increase just by avoiding that divider, which was preventing our loop from being properly vectorized. Did I type any of that in? I did not. You will notice that this is completely scalar. I never mentioned anything about doing this wide. The compiler just knows once it sees something it can vectorize, it's going to try, right? Loop vectorization is what you want.
Can I pause you just for 1 second? I'm sorry for pausing you. We just got a raid from Study Time. Hey, Study Time, thank you very much for the raid. Casey, can you switch back to the original code just for 1 quick second so people can see it? So this is the original code. There's this big thing going on that is a benchmark comparison test between languages saying, hey, this language is much, much faster. No, this language is much, much faster. Thank you for everyone's calling it a furry raid. Let's go. I can get a couple cats out. We can make it into a furry raid. But Casey's wicked smart, right? And so this code right here, now can you show the other code? This other code that you're seeing, which looks more complex, even erasing that just looks more complex. One wouldn't know, but this code right here runs 4 times as fast as the previous one due to how the compiler can optimize it and all that. And he's going to show how, or he's been showing how, some of these micro benchmarks, like you don't realize what is actually happening underneath the hood. And so it just seems like, oh, this one is this fast, or oh no, C's not all that fast. But really what's actually happening is you're just not writing good code. And he's just proven that these tests aren't really actually showing what you think they're showing. You're actually showing you defeating the compiler more than what the compiler is designed to do. And this, for me, I just would never have guessed doing a bunch of casting, doing all that, truncating, all this would actually be significantly faster than the other way around. So this is just mind-blowing for me.
So what we see here, is just like, look, if you've got an integer modulus in here, you're basically destroying any compiler's ability to do anything with your loop just right there. And so, again, compilers can do very creative stuff if they know what the actual integer modulus value is. So, for example, if they knew that u was going to be equal to 17 even a non-power of 2 number, they can then do something very creative here by turning that into a special series of operations that compute the modulus without actually having to do a divide. But if that number is unknown, as they have forced it to be here, all bets are off, and that is just all that is what will dominate the entire runtime of the loop, will be that integer modulus. And so breaking it into something that the CPU can do natively and can do wide, which I did here, where we just break it into something where I compute a 32-bit integer modulus by just using 64-bit floating point math. Paradoxically, right, you would not think that that would speed it up, but because integer modulus is such a special purpose operation that is slow on the CPU, doing so actually speeds it up dramatically, because although, again, it is more instructions, those instructions can operate on 4 things at a time. On AVX 512, you would get an even bigger boost here, because then you could operate on 8 at a time, because the register widening happens again. So think Zen 5 right here. We would be, which I don't, this machine isn't. My machine downstairs is. I'm tempted to go run it on there. But so we are stuck with just AVX2 on the Skylake machine. You would expect an even bigger boost if you switched this to AVX 512, because then it will unroll the loop and do 8, not unroll, it will vectorize the loop at 8 wide, still probably do, 4 unrolls or something, but it'll go 8 wide at that time, and you'll get another doubling of your performance there, probably. Depends
Wow.
on
some level of double, approximately.
Yeah. Sometimes they have to down clock, like you can't run at the same clock speed when you're running AVX 512 code. There's some things like that you have sort of restrictions, but for the most part, it is going to get faster, especially on Zen 5, which has single cycle AVX 512. So it's a beast. Zen 5 is an absolute monster. So yeah. So again, just to bring this back to the original point, why are we looking at all this stuff? Well, again, if you are going to be creating very small things that generally would be classified as a micro benchmark, which this sort of is, they really cannot be used for things like language comparison. That is not what you should be doing with this. As I just demonstrated, very small differences, even in the same language, with how you chose to phrase an operation will dramatically affect what the compiler can do. So as a language comparison, it simply doesn't make sense. The only time you want to be using micro benchmarks is for exploratory purposes. So you are trying to determine something about what the language is doing. Like, this benchmark makes perfect sense if what I was trying to do is explore the ramifications of having an integer modulus in my code, right? Now, all of a sudden, it makes perfect sense why I've created this benchmark. So exploratory purposes, fine. Or an expert doing a demonstration, right? If someone wants to say, I'm trying to demonstrate this thing to you, I've created these little benchmarks, let me show you how it works, totally valid. Not valid is, let me compare these two things and tell you about whether you should use one or the other one, or whether one is good or not, or rank them in a list like that. This is a completely inappropriate way to do that. And the reason is because of all of these things. Imagine a language, Lua would be one, for example, and I'm actually kind of surprised that it didn't do better on the benchmark. I wonder if there's something else going on, like because startup time is too expensive or something else like that. There are languages that define everything as happening in double. Well, if this was happening in double, Lua could have gone 4 wide automatically on this thing. So actually, Lua could have been at the top of that list probably if they had put in the right arguments. Like, my guess is the only reason someone didn't come up with Lua as being the fastest language is because someone screwed up how they ran the test, or maybe the compiler at the outset is too slow or something like that, right? But in general, this is why you don't do this.
And by the way, that would have been hilarious, making Lua at the top. That
would have been awesome.
Because people would have just, like, the amount of people going, I don't even understand the universe, it would have just been beautiful.
I wish it had. Because
Casey,
that's how
you
bad
could still make it happen.
Why are you looking at me, Prime? This is your kind of deal. Why don't you try to get this code submitted? See if you can get this. I'll send it to you if you want to try and sneak it in.
The problem is that there's video evidence of it, of us talking about it.
I know.
Then it'll be just a new race. You'll just open up a new race.
Yeah, well, that's what it already is in a way.
You know what the worst part is you may remember this from way back in the day, but in like JavaScript land, if you had an array, you'd set length to 0 instead of creating a new array, because it was actually much, much faster just to reuse your array.
Okay.
And saying, like, all these like incantations you would kind of come up with were ways in which you could do stuff faster. Guarantee you there'd be an NPM package by the end of this afternoon called fastdiv that people would use instead, that you'd call a function to divide by swiftly. It wouldn't work, but nonetheless, you would see these type of like these things crop up all over the world, being like, "Oh, this is the secret way to do it."
Yep. I mean,
it's actually more dangerous for people to know this, because we will then have NPM packages to deal with.
Look, this is why I stay out of those things. I stay out. I try to come on to streams and explain to people not to do these things. That is where my responsibility ends. Afterwards, you guys can left pad everything if that's what you think should happen. I don't want to get involved.
It's true. Okay. I actually agree with you. You just provide the tools, but you tell them to be used responsibly.
And or irresponsibly. I don't know. Do what you have to do. Yeah. So that's it. I think we've covered just about it. Unless anyone has any questions, but
That is just wild.
That
Yeah,
was
if anyone
all I
has any
wanted to
questions, I can be glad to kind of throw up some questions and see what people have to say about all this. Just because it's kind of curious. I got some people running up here, but if not, we can always I can always walk you through some sweet emoji code.
Yeah, yeah. Okay, you know what? Let me switch. Well, I guess if anyone has any questions.
Oh,
As soon
Luigit
as
was
they
faster
don't-
than Go, by the way, which is also, I swear they're doing something wrong with Go. Now, like, I'm upset about it because Go is a compiled thing. So it should, you shouldn't be tripping up the garbage collection, which should make it run that slow. There should be nothing to it other than just running compiled code. So it should be like reasonably close to something like Rust or C. I would just assume there's very little runtime. There's that slight runtime initialization overhead, and then everything else should be, or slight. Maybe that's why it's not. Maybe it's actually not so slight as I think it is. Maybe that's all it's really showing me is that Go's overhead to initialize the environment is much higher than I thought.
Yeah, I mean, all languages that have a heavy startup cost are going to get seriously penalized in this benchmark because the amount of work being done, again, is not very much. So the overhead of just starting up, if your language does a bunch of prep work before starting, that's really bad, right? In this benchmark.
Yeah, because this benchmark does not time the loop. It times the entirety from starting the program through the loop to the print statement.
Correct.
So obtaining your standard out and depending on how it prints out could also, you're also like console.log does something different than process.standardout.write. So I assume it does.
Even the code that's creating ASCII from an integer, that's measured here, right?
Mm-hmm.
Like all of it's measured.
That's crazy.
Yeah.
Let's see. Someone is saying, let's see. We don't have to consider cache hits and branch predictions in this case, right?
Yeah, for some unknown reason, and I guess I don't really know why, they did make this particular array slightly larger than the L1 cache on many x64 machines, but it is not larger than the L1 cache on the Mac he was running it on, which means this entire thing is in the cache. Like, this is 10,000 4-byte integers, or 40K. And I believe the M series has a 64K L1 data cache. I don't really remember, but I think it's like that. So technically this whole thing will be in the cache anyway. And even if it wasn't, it wouldn't really matter because this, despite the fact that it looks like it's doing writes here, it's not actually, because the compiler knows these are not marked as volatile or anything. So the compiler is under no obligation to actually flush them. And as we see back in the code here, it doesn't. Let me grab the. This was the original, right? The original code for the thing, and you can see it does everything. Excuse me. It does everything in such a way as to avoid actually doing the write back, right? It's like just kind of summing it in place. So it has to do loads here, but it doesn't have to generate any write traffic. So as long as these were being serviced on the order of the speed of this modulus, you'd probably be fine. But like I said, in this case, they should generally be, I mean, they're all going to be in the cache, and this loop is looping over the same ones. So the miss would only be right at the beginning anyway. This, again, it's the weird thing. You would expect this to be J, wouldn't you? I mean, you know what I mean? You would expect these to be flipped and this to be J, so that you were having
going
memory
through
traffic
the cache.
in there.
Yeah, you're not summing up a specific spot. Yes.
But it's not, and so it's like, let's suppose I got a cache miss because it doesn't all fit. So we clear them all out, and then we go back to the beginning, and now we're going to get a cache miss. Well, I'll miss the first time, but I'm looping 100,000 times, and so these will all be in the cache then, right? So, yeah.
Yeah, I assume the 10,000 was because 10,000 is a number. I don't think there was some sort of scientific and or like really direct thought through of like, oh, this is what the L1 cache size is.
So yeah, but anyway, that's kind of a long-winded way of saying cache misses I wouldn't expect to really have any effect here. I don't think they would matter just because of the way that they've structured it. Doesn't really rely on any kind of random access pattern that's pulling things in or anything like that. And the other thing is, in this particular case, they asked about branch mispredictions. There really are no branches other than the loop. So they're always going to be perfectly predicted because pretty much they're going to run 9,999 times correctly and one misprediction for the outer loop, right? And 99,999 times correctly and one misprediction for the inner loop, right?
Yeah.
So you wouldn't really expect branch mispredictions, even for a fairly crappy branch mispredictor. You wouldn't really expect it to have any problem. So,
okay. I guess so. Here's a question that I just see frequently showing up on the chat, which is, if you had to make a language comparison performance thing, how would you go about it?
I mean, I think the reason we don't really have something like that is because it's very difficult to make something that's actually useful. And the reason it's difficult is because what you want is very much like I was talking about at the very beginning of the stream when I mentioned like Gamers Nexus, Hardware Unboxed, those kind of channels that do like, hey, I'm going to run this entire game or these segments of these games, and I'm going to run that whole thing, measure its frames per second, what the 1% lows are, all that stuff, gather that for 40 games, and then here's a big chart. That's a pretty good benchmark for comparison purposes, right? For languages, ideally, we would want something similar, right? We want something where we're basically going to say, like, here's a real thing we care about doing. It's an HTTPS server, and we're going to serve this many client requests, this specific set of client requests or whatever, right? And we got to get back actual answers from actual files on the drive and all that stuff. You would want a bunch of workloads like that you run, and you go, when you write these in these languages, here's what you actually get. And the reason why I think that's really difficult is in order to be good, they have to be not toy, right? You have to actually develop a whole like HTTPS server or something in there, right? And it can't all just be, you know, opening OpenSSL or something, because then it's all just benchmarking C, because that's all written in C++ or something, right? So you have to make a bunch of code in these languages, and you know, no one wants to do that. They would rather do this, right? So I think it's pretty hard to make a good language comparison. Hard may be the wrong word. Time consuming. It's a lot of work. It's a lot of elbow grease for people to put in creating these things. And then you also have to have some kind of an idea of how you're going to keep that fair. If the programmer who wrote your Rust code is very good at writing efficient Rust code, but the programmer who writes your Go code is just really bad, right? That makes Go look like it's not very good, right? But that's not true.
Yeah.
So you have a lot of problems. So I think the reason we haven't seen a good one is because it's very, very difficult. It's a very, very difficult question to ask, and I'm not sure. I'm not sure I'd expect to see. I think you have to do a more targeted assessment yourself if you really want to know which languages are better at something for you.
And I think like what you said with the Gamer Nexus stuff kind of shows how unfair it is, because with the Gamer Nexus stuff, if you take a game and you run a specific path all the way through the game, you're going to get generally the same things computed each time. And you're only changing out the underlying hardware. Whereas this is like, you could see even with just how you wrote it, you being more talented with the old C, you were able to write it in such a way that's probably it's considerably different than the rest of the exercises showed, but you were able to be much faster because you knew all these tricks. And so it's just like each one of the shapes are even going to be fundamentally different how people are writing the code if they wrote it specific for their language. So it's not like you're testing the same thing on different speeds and memory. Instead, you're actually testing different things, potentially on the same CPU or maybe even different CPUs. You can get like all sorts of crazy results. There's an area of differences as opposed to just like a line of differences.
Yeah, and you know, that's why I say like I'm just not sure, especially because half these languages go through LLVM backend anyway, right? Like it's like their code gen is actually the same, and it's just a question of what the semantics are that you're putting in that gets fed to that code gen, right?
Mm-hmm.
So you end up with, it's a difficult problem if you actually wanted to solve it. I don't blame them for not solving it, but I wish they just wouldn't do this sort of thing. If you do want to interrogate how do loops work in various languages, so let maybe take an easier case. Let's say we wanted to talk about how inefficient are loops in languages generally, don't do this. Just do some disassemblies of what the loops invariance like maintenance code is and show it. Be like, oh, here's how, I mean, I've done this for Python before on Computer Enhanced. One of the things we do, right? I take the Python code to add two numbers together, right? A plus B, that's it. C equals A plus B. And I show like, oh, well, Python goes through, 100 some odd instructions just to do that instead of the one instruction it would take in, a normal language. That's useful to people. It's like, oh, okay, when I'm running interpreted Python, I'm in trouble, right? I really should be thinking, if I actually care about this, I need to use some kind of compiled Python alternative because it's going to be really costly to do anything in Python proper. So, just having that frame of reference, that's pretty valuable. And again, you can do that just by looking at what happens. You don't have to create a little synthetic benchmark like this that's, misleading.
I think TJ said it really well, which is I think it also doesn't show it well because if you spend 1,000 hours making one benchmark fast, doesn't mean that the easy idiomatic code is also fast. They don't compare really at all. So it doesn't even translate to production code really because maybe no one writes the optimized version of Go or C or whatever in real life. Yeah, it's because you have constraints. You have things you need to get done. You have to move fast. This is very different, two different mentalities going on here too.
Well, and I would use that comment, which is very accurate, to underscore something we've said, but we'll say it again because I think it's very important. Intentionally thwarting the compiler's optimizations, which is what this benchmark is designed to do, the way they've written it, is bad. Because what the average programmer actually wants is to know that the compiler will be doing those optimizations for them, right? The whole point is you don't want to have to think about what the most efficient way is to add a bunch of things together in a loop. You want the compiler to come in and go like, oh, I got you, buddy, and fix that up for you. That's the actual value add to you as a programmer, is not having to know what the correct way was to structure that thing. And so by benchmarking effectively, how do we prevent these compilers from doing a good job? You're taking away almost the only thing that the average programmer actually would want to know about looping, which is, will the compiler step in and help me if I write something fairly obvious? Will it be able to just know, oh, let me do the clever thing for you there, right? Yeah. And they've effectively said, no, compiler, you can't, don't do that. And that,
yeah, that actually makes a lot of sense. It's like the inverse of it all, which is that it's not making it clear or obvious what our goal is.
It's the inverse. Yeah. Yes. It's the inverse of what you actually would want to know about the compiler's loop behavior. So
it's crazy. Well, hey, I appreciate this. I'm very glad we got to do this.
Me too. Thanks for having me back on. I really appreciate it. And I was excited for this one because I was pretty upset about that benchmark. I don't know how seriously people actually were taking it, but I was like, oh man, I hope people aren't.
It made it to LinkedIn. It made it to LinkedIn, so you already know that there has been internal talks and stuff like that.
Oh no!
People have probably switched from Node to Bun, or are in the attempt of switching from Node to Bun, and not writing something in Go, because they looked at this benchmark and saw that, in fact, if you really do look at it, here I'm going to make you small. If you really do look at it, Bun is in fact faster than Go. So like something like this has happened, like someone has used this at least once. This has happened. It just can't even help it. It's just a part of life.
Oh god. Okay. Well, yeah. I mean, I don't have opinions about things like Node versus Bun or anything like that, right? But what I do have opinions on is, please don't use this benchmark for that.
Yeah.
This benchmark should not be used for anything. It's not a useful benchmark. It should be disregarded completely.